Hi, today's section of notes is 9.3. It's continuous growth or decay. And the difference there is going to be this word continuous. And one of the big things is people just get this confused with the stuff before on the first quiz, on the test, they'll do all the same equation. But if you see that word continuous or continuously in a problem, you need to go with what we learn in today's notes, whether it be growth or decay. Something that's not really in your notes, I wanted to jump ahead to this equation here. So I wouldn't write this down, but want to kind of show what's the point, what's really happening with continuous growth or continuous decay. Continuous growth, at least, we talked about this in investing money, where this is your principal, the amount that you put in, R is your interest rate, N is the number of compoundings, number of times you get interest in a year, and those are both the N's, and then T is the time. So what's really happening with this continuous growth and decay stuff? Let me jump over here to my graphing calculator. What I did here was I put in an equation. So I have a 1 for my principal, my starting amount. You could say that's $1,000. You could say it's $1. But what happens if you put in, maybe we'll say $1,000 at 5% interest compounded annually? That's going to be my first equation here. Well, when we do that, we get a curve that looks like this. You start out at your $1,000 and it goes up gradually at first and steeper and steeper and steeper, which is why I'm telling people invest early in your retirement. So your money isn't going up this fast when you retire. That's been in there longer has a chance to grow to a lot of money. Well, if we were to take and compound that more often, so if I go over here and also have my second equation, so this now my N value is 4, so 4 compoundings a year. As one would guess, you should get more money. You see a second line kind of appear a little bit above the other. And I'm just going to get these other two active as well. And I'm going to skip monthly and say, well, what about daily? If we compound interest daily, what's that going to look like? You'll notice I'm dividing by 365 days in a year. And this last one is the number of seconds in a year. So I have like 3,150,000 plus change, I think it was. No, 31,536,000 seconds in a year. And now if we were to graph all those, the lines pretty much look like they're on top of each other. You see they drew the third line, see they drew the fourth line. You can't really see the fourth line. But if instead of looking at that full 0 to 50 for the number of years, I just want to look from my 43rd year to my 46th year. And now if we go back and graph, you'll see them come up in order. So there's my first one, compounded annually. My second one, compounded quarterly. That would be the daily. And then the secondly one is pretty much like right on top of the daily. You really don't see a difference there. My point that I'm trying to make is as you compound interest more often, it doesn't matter. Well, you get a big jump going from like annually to 4 times a year, which seems odd. Your biggest jump would be there when you're only going up by like 4 times as often. When you go from quarterly, 4 times a year, to 365, you have this slight increase. And when you go from each day to each second, 1,001, 1,002, there's tons of seconds in a day. You still essentially have that same amount of money. It's right on top of each other. And that's where we get this continuous growth or decay. That you get to a point where it doesn't matter if you're compounding your interest every second, every millionth of a second, you reach a limit to how fast things go up. So when you see that word continuous or continuously, that's going to give you the equation for kind of that limit. It doesn't matter if you do it every or 2 billion times a second. You really don't end up with anything more than if you did 1 million times a second. So my formula then, I like to think of it as the PERT equation, so A equals P. Now the E is going to be this lowercase letter e, and it's kind of in italicized if it's ever in print. And the RT is the exponent. Kind of an embarrassing story for myself, perhaps, that maybe would help you remember it. PERT Plus, I don't know if you've ever seen it on the shelf. It's a type of shampoo. It's a big deal back when I was a kid. I think it was the first product that combined the shampoo and the conditioner. My parents bought it. I was allergic to it. I got red bumps basically from head down to my abdomen by the time it got washed out enough so I didn't have this rash on my body. So I do not use this, but maybe that'll help you remember PERT, P-E to the RT power. Want to comment on E. E is called the natural number, or sometimes it's called a Euler's number. It was first discovered back in the late 1600s or 1700s. And if you look at your graphing calculator, you should have over, let grab this. Right over here you'll see you have this ln button, and up above it you have this e to the x, because e is often taken to some power. So this button here is going to be the one you use. So you'll hit your second key, then you'll hit your ln key, your natural log key. If you just want e, you could just do second and then your division key over here and just get the e. But you also could do second natural log and then just put in a 1 for e to the first power. So, alright, back to here. So the equation then is a equals p times e to the rt. E, maybe I should comment on that before I go much further. E is the natural number, and the reason they call it that is because it just naturally shows up in nature in a lot of different things. This here, continuous growth decay, is going to be one of them. It also shows up in Newton's law of cooling, how fast you lose heat from a house. I, as a Christian, like to think of it as a number that's just kind of woven into the fabric of the universe, just like pi. It's a number that just kind of shows up. So I think when God made the universe, He put that number in there. But this here, let me write out what the different letters mean. So P then is going to be my principal, at least if it's money. Essentially it's really just the starting amount. And then E is just that natural number, so it's a natural number. And if you were to punch that in your calculator, e to the first, or e, you get like 2.718281828. Like pi, it's irrational. It's a number that just keeps going forever. They're trying to find the end of it still, some think tank somewhere. It doesn't repeat. It doesn't terminate. So it's the natural number. R then is going to be the, what do I want to call it, interest rate? Yeah, I guess interest rate. And after 2 lessons of trying to pound into your head, they need to do, for B, it needs to be 1 plus the number of its exponential growth, or 1 minus the number of its exponential decay. You're not going to get that here. You don't do 1 plus the percent ever. Instead, so maybe I'll actually write that in here, it's not 1 plus R. Instead, if you have growth, R equals the positive percent. And that's going to be in decimal. I'm going to leave a little space here so I can put down an example. If it's continuous decay, R is going to equal the negative percent. And that's going to be the percent also in decimal form. 2 quick examples, I'll toss them in there maybe. We'll say if something's going up by 12.5% a year, then R is just going to be, move the decimal 2 places, 0.125. For the exponential decay or continuous decay, if you have something going down by 6%, it's not going to be 1 minus 0.06. Instead, R is just going to be negative 0.06. Move the decimal 2 places. And T then, the last thing, is the time. And I probably shouldn't put this in there. I'm going to write in years. But it's really going to be the time unit that's going to be the same as this here. If they're saying something's going up by 12.5% per day, then T rather should really be your number of days. But often they'll talk about so much growth or so much decay a year. I want to do one example, and that'll finish up the notes on this section. If you think back to the notes we had on exponential decay, it's really the same example with a little change. So Santa bought a new sleigh 100 years ago to account for a population increase. If you paid $4,000 and the sleigh depreciates by 3%, before we said each year. Now I changed that and I put continuously, what's it worth now? And on the quizzes, on tests, in life, you may need to pay attention. If as soon as you see that word continuously, you can't do the y equals a times b to the x. Instead, you have to go with the PERT equation. So a equals p times e to the rt power. And p then is our principal. It's our starting amount. So the sleigh originally was worth $4,000. That's going to be my p. Then I have that times e to the RT. So we're now depreciating by 3%. Because it's depreciation, it'll be negative 0.03 times T, which would be the time in years, it's been 100 years, so negative 0.03 times 100. If I wasn't trying to do this in front of people, I'd probably just do that in my head. You're welcome to do that. If you have the older operating system, like I've been saying, make sure you put your exponent in parentheses. I shouldn't have to do that with the new Texas Instrument calculator though. I do 4,000. And then I could just do second and then my ln, my natural log button, to get the E. With this newer operating system, I can just punch in negative 0.03 times 100. Hit enter. And if it's decaying continuously, Santa's sleigh then is worth $199.15. So if I go back here, answer would be $199.15. So you maybe notice, if you remember the number that it was worth in section 2's notes, it was worth more than this. It's kind of something I find interesting. If it's exponential growth and continuous growth, it's going to be kind of the upper limit. When you have exponential decay or continuous decay, it doesn't actually decay quite as fast when you're decaying continuously. That is it for 9.3.